Hi everyone, so this is the video for the Unit 3 Big Picture, the Unit 3 Discovery Lab. And it does look a little bit different today. Instead of doing it on the big board, I had to do it on my computer with just looking at my notes. So do make sure that you actually watch the video and hear the explanation rather than just looking at the notes. Because as we know, there's a lot of explanation and kind of background work that goes into what we see. So starting with what we saw when we sent the trolley down the ramp, everybody pretty much had the same hypothesis that the trolley was speeding up. So this top opening parabolic relationship actually proves that it did speed up, because we're no longer seeing a linear trend that over time we're traveling the exact same distance, but we're seeing that more and more distance is covered in the same amount of time. Therefore, it has to be getting faster. So I did tell you that I wanted you to form the mathematical model for the poly, or this top opening graph, and I want you to kind of hold on to that for a second. Let's go ahead and work with the linear first and see kind of how far we can get with the linear approach. So knowing that it's a top opening, we have to go ahead and square the x values, giving us x squared second squared versus that position function, and now we get the linear trend. So moving on to making the model, we know that we start with y equals mx plus b because this one is the linear. So we can use the y equals mx plus b. We cannot use that for the poly. So we go ahead and plug in the fact that y is going to represent position, but what position? The final. B, remember, yes, it's the y-intercept, but it has a much bigger representation. It represents the initial position. And we saw in Unit 2 that if you have very distinctly different parts of your graph, that initial position is going to change when you make your model. So try to get away from thinking y-intercept and always be thinking initial position. So we plug in the fact that x is time squared, and then we move on to the slope because that's really kind of our main focus. That's showing how these two variables are interacting. So in order to solve for the slope, we know that it's change in y over change in x, which represents a change in position over a change in time squared, which really just isn't that descriptive. Okay, position over time squared. What does that mean? So we can take it one step further and we could look at the units, and we see meters per second squared. And it might be starting to jog some thoughts, especially if you had calculus. You may be thinking, okay, well, I've seen this before. But the fact of the matter is even if we've seen it before, meters per second squared really still only goes back to position over time squared, which isn't really a definition that is helpful. So what I'd like you to do is, like what I said here, I want you to pause and just kind of keep this for now, because we can't define anything because this is missing velocity. We know that velocity is meter per second, and right now, none of this is dealing with velocity. So if your hypothesis was looking at a change in velocity, this isn't helpful. So we kind of say, well, what can we do next? What other tools are in our toolbox? So we did the linearization approach and said, okay, well, this is as far as we can go. We also know that we could take the area under the curve, but that's not going to work because this is a position graph and you can't really go back any further. But we do know that we could take the slope of the line and get the velocity, right? So when we look at this, one thing that we kind of immediately have to realize is, okay, well, we know that the slope of a position versus time graph is velocity, but this is a top opening parabolic relationship. This is a curving trend. This is not something that's linear. So you can't just take the first and last point and do the slope and say, oh, this is the velocity, because it's not. It's the average velocity over those 2 points. But this is showing a constantly changing velocity. So if you were to take the slope down here, you're going to get a very different value than if you were to take the slope up here. So that's where we have to move into, how do we make a velocity versus time graph? So that's our step 2. And what we would have to do is we would have to break down this ever-changing slope into smaller and smaller and smaller time intervals. So that's kind of the first thing that I say is we know the slope is velocity, and then the second thing we have to do is break it up. Because if you take it in smaller and smaller and smaller chunks, then you get a velocity that is a little bit more indicative of that section. But here's the thing, even if you take the slope of these smaller and smaller and smaller sections, we still have to be able to plot that velocity with a time, because we can't make what would look almost like a stepwise function. We're not going to have horizontal lines for our velocity graph, not when it's changing like this, because the reason that we had the horizontal lines was because we had a constant velocity, but we don't have that anymore. We have a changing slope, so we have a changing velocity. So what you've pretty much done when you take the velocity of those smaller and smaller and smaller sections is you've taken the average. Well, where does the average occur? You know, if we were to line everybody up in the room by height, the average height person would be in the middle. So we get this concept of instantaneous velocity because we have to plot something. And all we know are brief instances in time when the velocity is actually the value that we calculated. So this instantaneous velocity is that average velocity plotted at the midpoint time. So really, you don't have to do anything crazy different with Unit 3. You just have to do it more often. So what you would end up doing is you would create a brand new table. You would create, okay, well, what are the midpoint times of the different sections that you broke off? So maybe this is 0 to 1 second, 2 second, 3 second, 4 second, and 5 second. So then when you would take the slope of the first section, you would get that average velocity, which would go into your y column. And then if the time was 0 to 1, well, then the midpoint time is 0.5. So you would be plotting 0.5 versus whatever you calculated. And when you would do that for all of those different sections, and again, kind of already in the back of your mind saying, oh, this is getting more and more steep, the velocity has to be bigger, building off of what we did in Unit 2, you do indeed get a linear trend. And I know that in Unit 2, one of our rules was that you could have no linear lines on the velocity versus time, but that was because we had a constant velocity, and now we have a changing velocity. So we should see those points being plotted, and they will form linear lines. Well, now the fact that, you broke everything up, you took the slope, you graphed it with the midpoint time, you got this linear trend, we can make a model with a linear trend. So then knowing that, we have our model is y equals mx plus b. Y is now going to represent velocity, but just like before, it's going to be the final velocity or whatever you get to. We are going to hold off on the slope for just a second because we're going to see it down here. We have time representing our x, and then our b is going to represent our initial velocity. And in this case, the initial velocity was 0, but it doesn't always have to be 0. Then we go down to our slope and see delta y over delta x, which is indeed a change in velocity over a change in time. And when you break down those units, now we're finally getting meter per second squared. So our definition is indeed that acceleration is a change in velocity over a change in time. So a is equal to delta v over delta t, and this is a vector function. That was something that came up with the whiteboarding questions. Because velocity is a vector, acceleration is going to be a vector. That's going to have a direction and magnitude as well. But now the question becomes, well, I still don't have a position equation because x is equal to at squared plus the xi. still isn't quite good enough. So even though we know that the slope is equal to the acceleration, this equation is still missing velocity. It's still not putting together all of the pieces that we need, and we need models that have all of the pieces because you're trying to represent any case possible. So any case involves position, velocity, and acceleration. So that's where we say, okay, well, the only other tool that we haven't used, we've used linearization, we took the slope, is to take the area. And I said in Unit 2, this is something that is very, very, very helpful, but it's often forgotten. So if we were to take the area under the curve, which is what we're going to go ahead and do in Step 3, one thing we have to do is we do have to give ourselves a kind of a new graph to look at. Because although this is what we saw, the velocity was 0 there. But we could have an initial velocity that's not 0. So if we're trying to create an equation that is useful for all cases, well, then we need to break down a graph that incorporates all cases. So we can just go ahead and move our line up to some initial velocity. And we know that if we take the area under the curve, it is indeed displacement. And when you move that line up, we end up having to break this up into two different sections. So we break it up into taking the area under the triangle, and then we take it with the rectangle. So we end up getting 1/2 base times height for your triangle, and then your number 2 is going to be the length times the width. So if we do 1/2 base times height, we get 1/2 multiplied by time multiplied by the height, which is delta V, and then we get VI multiplied by T in our second section. And all of that is going to be added together to form that displacement. So when we do section 1 plus section 2 is equal to delta x, we get the 1/2 delta V times T plus VIT is equal to delta x. But again, we get here and we're like, no, the whole point of this was to get to acceleration, and there's no acceleration, so this still isn't good enough. But if we kind of look aside and we say, okay, well, acceleration is delta V divided by T, well, then we can rearrange the fact that delta V is going to be equal to A times T. So we can go ahead and substitute that in, giving us 1/2 AT times T plus VIT is equal to delta X, which breaks down to 1/2 AT squared plus VIT is equal to delta X. Now do remember that delta X, which is your displacement, is equal to XF minus XI, meaning that we can add the XI over. And now this looks an awful lot like what you got for your polynomial trend. You had an x squared, you had an x, and then you had a number that was all by itself. And many, many times it was brought up that, we think that the acceleration is in there, the velocity is in there, and you were right. Your first portion of that equation was 1/2 multiplied by your A. The number with your x was indeed the initial velocity, and then the last value was indeed the initial position. And many of you did see that VI being very, very, very little, almost getting to 0, and then same thing with your XI. So that's kind of how everything comes together, looking at, why did I make you do the poly equation? Well, here it is. Here's how it connects. So it was kind of a final thing to write down. We do have 3 equations at this point, and they are distinctly different equations. If you are dealing with uniform acceleration, you can only use uniform acceleration equations. You cannot use constant velocity. They are 2 very different motions, and very different motions have distinctly different equations. All right, so I'm going to do an example, but that will be in the next video.